We're going to be looking at car stopping distances. Stopping distance is defined as the distance travelled by a car from seeing the need to stop to when it actually comes to a stop. And it's determined by adding the thinking distance with the braking distance. And the thinking distance is the distance travelled by the car while the driver is reacting to apply the brakes. It is not the time taken for the driver to react to apply the brakes, because a distance is not a measurement of time. And during the thinking distance, the car is maintaining its speed, so it's travelling at a constant speed. Braking distance is the distance travelled by the car while the brakes are being applied until the car comes to a stop. During the braking distance, the car is decelerating, and to keep the calculation simple, we will assume a uniform deceleration, and so that means we can use the equations of uniform acceleration, that is, the Suvat equations. We can also plot a velocity time graph to show the motion of the car. So at time equals 0 represents the time when the driver sees the need to stop, for example, approaching red traffic light. So we initially have a constant velocity while the driver is reacting to apply the brakes, and then the car decelerates when the brakes are applied. And this time here represents the reaction time of the driver, and the area under a velocity time graph represents the displacement or the distance travelled. So the area under the first part of the graph, the rectangle, represents the thinking distance, and the area under the second part of the graph, the triangle, represents the braking distance, and adding the two areas gives you the stopping distance. The speed of the car affects both the thinking distance and the braking distance, and the car that is travelling at a greater speed will have a greater stopping distance. And that's because thinking distance is directly proportional to the speed if we assume that the reaction time of the driver is constant, and that comes from the equation S equals vt. The distance equals the speed multiplied by the reaction time. So if time is constant, then S is proportional to V. Also, braking distance is directly proportional to speed squared, assuming that the deceleration of the car is constant, and that comes from the equation v squared equals u squared plus 2as. V, which is the final velocity, will equal 0. So if you rearrange that equation to make S the subject, you get S is equal to minus u squared divided by 2a. So S is the braking distance, u is the initial speed of the car, and the minus a represents the deceleration of the car. And if a is constant, then S is proportional to u squared. It can also be explained in terms of energy. So the work done to stop the car will equal the loss in kinetic energy of the car. So work done equals force times distance moved in the direction of the force. So in this case, it's the braking force multiplied by the braking distance, and that will equal the loss in kinetic energy of the car. And if we assume a constant braking force, then you can see that S will be proportional to U squared. So thinking distance is directly proportional to speed. So if we use this equation where S is the thinking distance, B is the speed, and T is the reaction time of the driver, then when the speed equals 1 meters per second, then the thinking distance will equal T, because we've substituted V equals 1 into this equation. When the speed equals 2 meters per second, then S will equal 2T. And so we can see we've doubled the speed, so we've doubled the thinking distance. And when the speed equals 3 meters per second, then the thinking distance will equal 3T. So when we've tripled the speed, we've tripled the thinking distance. And this relationship is called directly proportional. So thinking distance is directly proportional to the speed. The thinking distance and speed are increasing by the same ratio, the same proportion. Braking distance is proportional to speed squared, where S is the braking distance, which is equal to the initial speed squared divided by 2 times the deceleration of the car, the minus A. So when speed equals 1 meters per second, we substitute U equals 1 here, we will get S is equal to minus 1 divided by 2A. When speed equals 2 meters per second, then the braking distance will equal minus 2 squared, which is 4, divided by 2A. So what you can see is when we've doubled the speed, the braking distance has quadrupled. When speed equals 3 meters per second, then the braking distance will equal minus 3 squared, which is 9, divided by 2A. So you can see when we have tripled the speed, we have 9 times the braking distance. So this is showing you that braking distance is proportional to speed squared. So if you double the speed, you'll have 2 squared, which is 4 times the braking distance. If you have 3 times the speed, then you will have 3 squared, which is 9 times the braking distance, and so on. So a drunk driver will have a longer stopping distance, and that's because drinking slows down the reaction time of the driver, and so you will have a longer thinking distance for a given speed at which the car is travelling at. So S equals Vt, our thinking distance equals the speed of the car multiplied by the reaction time of the driver. So for a given speed V, we can see that the thinking distance is proportional to the reaction time of the driver. So a longer reaction time, then a longer thinking distance. If we have a lorry and a car travelling at the same speed and the same braking force is applied, then the lorry will have a longer stopping distance. And that's because the lorry has more mass, so will have more kinetic energy, so more work needs to be done to stop the lorry. So you can see for the same speed U and same braking force F, the braking distance will be proportional to the mass. So you have the same braking force will be applied over a longer braking distance for a larger loss in kinetic energy for the lorry. Alternatively, because the lorry has a larger mass, we can say it will have a smaller deceleration for the same braking force, and that comes from F equals ma, where the deceleration will equal the braking force divided by the mass. So for the same braking force, a larger mass will have a smaller deceleration, and hence a longer braking distance. A car with worn brake discs will have a longer braking distance and hence a longer stopping distance, and that's because the worn brakes decreases the friction, the braking force that acts on the car, and so the car will have a smaller deceleration, and that comes from F equals ma, where F is the braking force and A would be the deceleration. A car with ball tyres on a wet day would have a longer braking distance and hence a longer stopping distance, and that's because the ball tyres, the contact is between the tyre and the layer of water between the tyre and the road, and so this reduces friction, so the braking force that acts on the car, so it will have less deceleration. Tread tyres, which have these grooves, clears away the layer of water on the road, and so you have better contact between the tyre and road to increase the friction, the braking force that acts on the car. A car along a level road will have a longer braking distance and hence a longer stopping distance than a car moving along a road with an upward gradient, and that's because the car moving along the upward gradient has a component of weight that is working with the braking force. They're both acting in the opposite direction to the motion of the car, and so this increases the resultant force on the car, so there'll be a greater deceleration on the car, so a shorter braking distance. In terms of energy, then the car moving upwards, some of the kinetic energy is converting into gravitational potential energy as the car gains height, and so it is losing kinetic energy, so less work is done to stop the car. The same braking force will be applied over a shorter braking distance. A car moving down a road with a downward gradient will have a longer braking distance and hence a longer stopping distance, and that's because it has a component of weight working against the braking force. The component of weight is acting in the direction of the motion of the car, but the braking force is acting in the opposite direction to the motion of the car, so that then the resultant force on the car will be less, so there'll be less deceleration on the car, so a longer braking distance. In terms of energy, gravitational potential energy is converting into kinetic energy as the car loses height, So as the car has more kinetic energy, more work is done to stop the car.